So myself Sanal Mohanan, I'm basically a mechanical engineer, and I did my masters from Applied Mechanics Department of IIT Madras. So I will discuss a little bit about UNS EduTech, then we'll go to the session. So UNS EduTech is actually, we are a group of people who are passionate about teaching, and we are using new methods in teaching, new methods in the sense like we are using a lot of activity based teaching. That is our speciality. We'll demonstrate a lot of activities, experiments, then animations will show, so that we'll try to teach the concepts a little more in-depth way. So that is our main objective, and you can for more details you can go to our website and you can read about us, and if anybody is interested you can directly call us and you can get more information. So anyway, welcome all of you to UNS EduTech's physics demo session, and we started a little late, really sorry for that. We apologize for that inconvenience caused, sorry for that. So today we will be discussing about an important topic. It will be a topic from plus 2 physics, and we are going to discuss about electromagnetic induction. So you can wait till end for your doubts. If anybody is having any doubts, okay, you can wait till the end. We'll allow some time at the end of the session so you can clarify your doubts. Okay, thank you. So we'll start. So here, you know that electromagnetic induction you might have studied in, you studied in class 10. Class 10 syllabus is there, electromagnetic induction. So in plus 2 you will be studying the extension of that. You already studied the basics, you already know what exactly is electromagnetic induction, and today we are going to discuss little more details. Then we'll go through the mathematical aspects of electromagnetic induction will be discussed, because that was not there in your 10th level. 10th level you are studying only in the qualitative way, and now we are going to quantitatively analyze the process of electromagnetic induction. So electromagnetic induction is nothing but, that is the reason that invention was done by Michael Faraday in 1831, and that is the reason why you are able to communicate today, because of electricity only you are able to communicate. And when you talk about electricity, there are two types of electricity. One is alternating electricity and another one is direct current, or alternating current or direct current. So Faraday's law of electromagnetic induction or electromagnetic induction has something to do with alternating current. Okay. Now before going to lot of details, I will directly take you to an experiment. Then you will understand that what exactly is electromagnetic induction. Then slowly, step by step, we will go to the mathematical aspects. Then we will try to solve some previous year questions as well. Okay. So I hope all of you are ready for the experiment. So here you can see that there is a galvanometer. Galvanometer is nothing but a device which can sense very feeble current. Even microamperes can be detected using galvanometer. And here this galvanometer is connected to a copper coil. Copper coil, copper resistance is very less, and any conductors, most of the conductors have a lot of free electrons inside. So here this copper coil is having a lot of free electrons, and the ends of this conductor is connected with the galvanometer. Okay. Now here I have a permanent magnet. This is a traditional magnet. This is the alloy of aluminum, nickel and cobalt. And you know that magnet means a device. This is special, it's basically an atomic property, and the origin of magnetism is basically you have to go to the electron spin around atoms. So if you have a magnet, bar magnet, there is a special property called magnetic field. There will be a magnetic field around this, or in a 3D shape there will be a magnetic field around this magnet, bar magnet. Now magnetic field is, you can say that magnetic field is nothing but the region of space around that particular body where the magnetic force is experienced. Okay. Now you can see that imaginary lines will be there, the magnetic fields are imaginary lines. Now if I am trying to bring this magnet into this coil, this magnetic field will be in touch, is in touch with the entire coil. Okay. So you can see that the magnetic field is in touch with the conductor, and there are electrons inside. These electrons are under the influence of the magnetic field generated by this bar magnet. Okay. Now all of you look at this galvanometer. You can see that if I move this magnet inside, you can see there is a deflection. So it's very interesting finding done by, so it was invented by Michael Faraday in 1831, and you can see that here when you are moving this magnetic field, the magnetic field is applying certain force on the free electrons inside this conductor, and that free electrons are flowing through the conductor. If the conductor is closed, if the circuit is closed in the sense it should be a loop, then only current will flow. It will flow from one location to the same, it will come back through the entire loop to that same location. So here if the circuit is closed, you can experience a deflection. That means a small amount of current is passing through this galvanometer. This phenomenon of generating electricity or the flow of electrons is called electromagnetic induction. Okay. Now, you can see here I used a permanent magnet. That is one method. So, one more thing is there. You know that whenever we see electricity and magnetism are always related. Electricity can generate magnetic field, or electric field can generate magnetic field, or magnetic field can produce electric field. So, they are interrelated. Now, if you have a coil, assume that you have a coil, and if you are sending a current through that, I have a battery here. If I am sending a current through that, we can say that become a magnet, because a current carrying conductor will behave like a magnet, or there is a magnetic field outside that conductor. Around that conductor there will be a magnetic field generated if you are conducting, if you are allowing current to pass through that. So, now instead of using this bar magnet, I can do one thing. This smaller coil I can insert into this larger coil. Okay. Now, I can connect this to a battery. See, this one I am connecting to a battery. Here if I connect that, you look at the galvanometer, you can see again it is deflecting. Okay. So, in two methods we can do this. See, one is, you can see, listen again. So, I am going to show this. So, here we discussed about two methods, two different methods. One method was inserting the magnet, permanent magnet into this so that the deflection is happening. The second method was inserting the coil, smaller coil into that magnet, in the larger magnet, and I am supplying some direct current, and if I am making and breaking the circuit, you can see certain deflection on the galvanometer. So, this shows the magnetic effect of electric current. Anyway, that is not a major thing which we are going to discuss today. Now, let us come back to here. See, another experiment. I mean, there is one more experiment. I am going to show that. Here, I have another coil and I have a powerful magnet. This is a neodymium magnet. It is very powerful compared to traditional Alnico magnet. So, here this magnet I am going to operate in the same way I am going to operate in this coil, and here there is a difference. I am connecting this circuit to a LED. LED is nothing but light emitting diode. So, if I operate this, you can see that, see, I am going to operate. See, light is generating. You can see that when current is flowing, light is generating in the circuit, and you can see deflection in the circuit. All of you watch closely. I am repeating again, if you are not able to see, because it is a live session, sometimes focusing will be difficult. So, look at this, see, you can see. Now, there is an interesting phenomenon. So, the same thing, the electricity is generated here also. Now, if I move very slowly, you are not able to see any light. But if I am moving fast, you can see bright light is coming, and if I move faster, the light become brighter. So, these are the things Faraday observed when he did this experiment. He found out that there is the amount of EMF generated, or the amount of voltage generated. Basically, you know that when this is deflecting, current is passing through the circuit. At the same time, you know, there is a deflection happening, sorry, the voltage is also showing. So, certain voltage is also there. Then you can say that, so basically EMF is generated. EMF is nothing but electromotive force. Electromotive force, see, don't deviated by that name. So, electromotive force is not a force, it is a misnomer. It is actually voltage generated, or the potential difference generated across the conductor. Now, Faraday was very keen on understanding what are the factors influencing this voltage generated or the EMF generated. So, here you can see the EMF generated is directly proportional to the number of turns. How many turns are there? You studied in class 10 itself, you studied about solenoid, electromagnet you studied. So, all of you know this. See, here if number of turns are more, the voltage generated will be more. Then the area of cross section also matters. If you have more area of cross section, the more the area cross section, more voltage will be generated. Then one more important thing here, the speed at which you are moving this. The speed at which you are moving the magnet means the speed at which the magnetic field, there is a quantity, that is a physical quantity which is experienced around this magnet, and the speed at which the relative motion is happening between the electrons or the conductor, simply the conductor, and the magnetic field. That these are the factors influencing this electromagnetic induction, I mean the voltage generated. So there is a quantitative explanation for that. That law, there are two laws associated with electromagnetic induction. The first one is called the Faraday's law of electromagnetic induction. Then second one is Lenz's law. The first one will give you the quantitative estimate for the amount of EMF generated in the circuit. Now the second one we are going to discuss after a while, so please wait for that, otherwise you will confuse. So here you have seen that the first law is nothing but a quantitative approach. The Faraday's first law, or Faraday's law of electromagnetic induction, usually is called Faraday's law of electromagnetic induction, and it is going to give you a mathematical estimate for the EMF generated. Okay, so I hope all of you understood the basics. I will go back to whiteboard, then you will understand more details. We are going to discuss a little more details, then you will get a better picture. Okay. See, if you are analyzing the details of a magnet, if you are taking a magnet, the field lines look like this. The field lines will be, if you are looking in the outside part, field lines look like starting from north and ending at south. It is not actually ending, it will be continuing from south to north inside that magnet. So a typical bar magnet field look like this. This is only for a plane. Actually it is a 3D structure. You can imagine that if the same structure is happening, or if you are rotating this structure, you can just imagine how it look like. It is actually a 3D structure. So this is how a typical magnetic field look like. Okay, and maximum concentration will be somewhere near the poles. These regions are called poles, and the B is nothing but the quantity called the magnetic field, or is a vector quantity. Remember, B is a vector quantity which have direction as well as magnitude. Now here I will show you a visualization. If you want to visualize, see how we know that, okay, this is how the magnetic field look like. So for that we can do some visualization. Here if you are sprinkling some iron powder on the top of this magnet, you can see this pattern. This pattern shows that near the poles, near the pole means the ends of this magnet, maximum density will be there, maximum the field density or the strength of the field will be maximum at the poles, and remaining region you can see these kind of structures you can see that shows that the field look like that. Okay, I hope all of you understood that part. Now we have to understand a very important parameter called magnetic flux. The flux is nothing but, if you are taking the poles, see this is a continuous magnet, here one south pole and north pole is there, here south pole and north pole is there. So this is a continuous magnet, and we are putting two magnets side by side. If that is the case, there will be lines of force. We can represent the magnetic field in the form of lines. So these are the line of forces, and here the flux is nothing but a quantity which is actually the product of the magnetic field into area. If you are considering certain area A, between that, assume that you are considering certain amount of area, and if you are multiplying the magnetic field into that area, that quantity is called magnetic flux, usually represented by phi b. Okay, magnetic flux is nothing but the magnetic field into area. If it is a straight, that is actually the actual definition we are going to cover now. Before that, you can see the magnetic flux is defined as B into area. Now remember, B is called magnetic field, its unit is Tesla. Okay, again a famous scientist named Nikola Tesla. He invented alternating current. So here the process he found out, but the commercial production of alternating current, everything was done by Tesla. So here T is nothing but the unit Tesla for magnetic field, area is having meter square unit. Now you can see that the unit of flux will be Tesla meter square, or there is a single unit for that, that is nothing but Weber. WB Weber is again another scientist name. So this is the basic explanation for magnetic flux. So this part, don't worry, you are going to study this. The chapter just before this you are going to study. Since this is a demo session, we are taking a short topic, and when you go in a sequence you will understand properly, don't worry much about that. So here you have a mathematical expression. Actually it's not simply B into area. See, B into area, the phi B is B into area is applicable for a simple case like previous case. You can see if it is the previous case, we are taking an area which is perpendicular to the magnetic field. If the magnetic field is perpendicular to that area, then you can simply apply B into A. Otherwise, if that is not the case, if you are taking an area which is at an angle, here the magnetic field is making an angle theta, here you can say theta with the vertical, then you know the flux definition is whatever magnetic field in the direction normal to the area vector. Area vector is nothing but, it's the first time you are studying, I hope. So area vector is nothing but the normal. If you are making a normal to the surface, if you are making a normal to the surface, you will get a vector called area vector, and usually we write a vector, okay, or A into an n cap, an unit vector in the direction perpendicular to that surface, that is called area vector. So we have to find out the field. If this is the magnetic field, you have to find out the projection, or you can say the B cos theta component will be nothing but along the perpendicular direction or along the normal of that surface. You can see that if I am taking the triangle, this is B, see this quantity is B, this will be B cos theta, okay. So that quantity will be B cos theta, okay. Now see, we can write down that flux will be equal to, okay, B cos theta into A. Now you know that if cos theta is coming between two quantities, you already studied, it is nothing but dot product. So we can write down in a simple form, we can write down B dot A, we can write. This is expression for magnetic flux. So flux is defined as B dot A. So we are finding out the quantity of field, or the number of field, the number density we can say, or the quantity of the magnetic field lines passing in the normal direction of an area is called flux. This is a magnetic flux, okay. We need this when we discuss about the Faraday's law, we need this idea. Now see, let us discuss the idea of Faraday's law. See, Faraday observed that the EMF generated, let us represent using the letter E. The EMF generated is proportional to the area of cross section, then EMF is proportional to, what else we discussed, the number of turns, N, then EMF is proportional to change in magnetic field with respect to time. So we can write down delta B divided by delta T, okay. So delta B by delta T is nothing but change in magnetic field. If you are bringing together all this, if you are considering all this relationship simultaneously, we will get a simple relationship. E will be equal to A into N into delta B divided by delta T. Now you already know that, see, you already know that if you are multiplying area into magnetic field, you are going to get magnetic flux. You can say that E will be equal to N into delta phi B, we can write down. This is nothing but magnetic flux divided by delta T, and this is for a simple short duration of time. If it is an infinitesimal time, then we can say N into d phi B by dt, okay. So the rate of change of flux with respect to time into the number of turns in that coil will give you the value of EMF generated or the voltage generated across that conductor. That is the idea. So here E will be equal to N into d phi B by dt. This will give you the quantitative value for the amount of EMF generated across that conductor. This law is called Faraday's first law or Faraday's law of, not first law, Faraday's law of electromagnetic induction. Sometimes you know we call it electromagnetic induction, two laws are there, first law, second law. First law is nothing but Faraday's first law or Faraday's law of electromagnetic induction. Then the second law is usually Lenz's law. It was found by some other scientist, one Russian scientist, Heinrich, actually I forgot exact name, Heinrich Emil, you can search about that. He found out the Lenz's law, Heinrich Emil. Okay, fine. Anyway, this is the idea behind Faraday's law of electromagnetic induction. Now, I'll do one thing. We will come back to this experiment, the first experiment. So here, I will show you there is one more important thing. Okay, all of you listen. Here, the same experiment I am repeating. You can see that in this magnet, this is not a colored magnet. You can see the north pole is represented by a small dot. Okay. Now, I am going to insert this north pole into this coil. Okay. Now, all of you look at this galvanometer. If I lift upward, you can see it is going towards the right side, and if I insert that back, you can see it is going towards the left side. It is very strange in the beginning. You can see that. Once again I will repeat. If I lift this magnet, it will go to the right side. If I insert, it will go to the left side. It is very strange. So this law has something to do with the second law, or the Lenz's law. So in order to understand Lenz's law, you have to understand some more thing. Here, previously you know about battery is source of energy, and here battery can provide electrical current. If you are connecting a loop, current will flow through that circuit. Now here you have to understand the generator, even though we call it generator, that is not a source of energy. Generator is actually not a source of energy, is a very, very important understanding. Generator is actually a device to convert mechanical energy into electrical energy. So when you do this magnet, if you are moving this magnet, you have to spend certain amount of work. For lifting this or moving this magnet inside this coil, you have to spend certain amount of work. That work is converted to, here that is converted to electrical energy. See, when you are doing that, all of you listen, this is a very key point, very important point in this experiment. So when you are moving, if you are entering north pole into the system, the current will be flowing, a current will be induced in this coil. That induced current will produce again another magnetic field that you already studied. You already know that in class 10 itself you studied when current is passing through a conductor, a magnetic field is generated. Now, when I am trying to move north pole into the circuit, the current induced in this coil at this end, if you are looking from this end, you can see that. If you are looking, you can see north pole is here. You can see, if I am inserting this north pole into this coil, you can see the current generated in this side will be in such a way that this side of the magnet will be north pole. You already know that in a solenoid, in class 10 you studied solenoid, depend upon the direction. See, I hope all of you remember this. Just a second. See, if you are looking from the side, if the loop, on a coil, on a coil like this, okay, if you are supplying current like this become a magnet, this become an electromagnet. In this case, when you are looking from here, if you are seeing this pattern, or if the current is flowing in the clockwise direction, then you can say that side become south pole. And if the current is going in the north direction, like anti-clockwise direction, then we can say this will be north pole. This is the symbol rule. See, this is actually a symbol, that empirical rule we followed. But here, when you do this experiment, if I am inserting north, the direction of the current will be in such a way that that side become north. And when it is north, north and north will repel. Like poles repel, unlike poles attract. That also you studied. Okay. Here, if I am inserting that, since north pole is generating because of the current flow, or we can say another magnetic flux or magnetic field is generated in the system, and that will try to oppose, and because of that there will be a resistance will be experienced, or that because of the resistance you have to do certain amount of work in order to move against that, and that work will be converted to electrical energy. So this device is a device which convert mechanical energy into electrical energy. That is a key concept you have to understand. And this Lenz's law will give you the direction. Direction in the sense, because of this conservation of energy, we can say that the direction of the current should be in that way, then only it will oppose. Then we can say that conversion, we are working against that generated flux, or we have to do certain amount of work to oppose that or to generate that electricity. Now, you can say that if I am trying to lift the north pole, what will happen? If I try to lift the north pole, you can say that that side become, the current flow will be changing, and that side will try to become south pole, and south pole will try to attract north pole. And basically, if you are looking from outside, we can say that, see, this system or altogether, this coil magnet system, if the coil is connected, if the coil is closed circuit, remember, if the coil are open, you will not experience this resistance, because current should flow. Then only the magnetic flux will be formed, otherwise potential will be there. Electron have a tendency to move, but it will never flow, and once the motion starts, then only you can experience this. So if the circuit is closed, if you are trying to move this magnet, the system will try to oppose any motion. The system will try to oppose the change in flux. That is the reason why you are getting a opposite deflection in this case, based on the direction of motion. So basically, you are getting a relationship, a qualitative relationship. In the previous case, you are getting a quantitative relationship about the quantity of EMF generated. Here you are getting a qualitative idea. Qualitative idea in the sense how it is varying. When one is changing, how is other change? When the magnetic field is changing, how the electric current is changing. That is our idea. So here, let me go back to whiteboard. See here, see, here we discussed about this equation. So here one important quantity was missing here. See, here Lenz's law says that the EMF induced will be in the opposite direction of the change in flux. Opposite direction in the sense is not physical direction. You have to understand that the variation, when one is increasing, other one is decreasing. That is the idea. So here this sign will be coming from the Lenz's law, or we can say Lenz's law is a consequence of law of conservation of energy. Okay. So all of you should put some effort to understand that part. It's not very easy. You have to read again and again, then only you will understand. So this negative sign is coming from law of conservation of energy, or Lenz's law, and that will give you an idea. The variation of EMF or induced current will be in the other direction of magnetic flux. I mean in terms of its increasing or decreasing. That is the idea. Okay. So this is the idea behind Lenz's law. Okay. I hope all of you understood this part. Now we can do one thing. I will take you to a simple simulation, not simulation, an animation, a 2D schematic animation I will show you, so that you will get some idea about what exactly happened here. Look here. Here I have a magnet. Okay. A coil. The coil is connected to bulb. Okay. Now if I move this, I can show you the field lines. Field lines look like this. If I move this magnet, you can see that bulb. Look at the bulb. If I move fast, you are getting a bright light. If I am moving slowly, the light is very, very feeble. So that means the faster the change in magnetic field, or the rate of change of magnetic field is more, then you can say that the light become bright. See here, if I move fast, look at that again, you can see that it's moving fast. Now let us see the Lenz's law as well. I mean this one you are getting the Faraday's law of electromagnetic induction. More speed, at least only one thing you can experience here, more the speed, brightness will be more. If I connect a voltmeter or a galvanometer, okay, with a central needle. So if north pole is going into the system, you look at that. In the previous experiment, it may not be visible clearly. Now you can see. That is why I am showing this animation as well. See here, if I am inserting north into this, you can see that the deflection was towards left. So look here, this is a schematic animation. First you can see that this is a magnetic field, there is a magnet, there is a magnetic field around that, and when you are bringing close to this coil, you can see the magnetic field is linked with that coil, and if I try to move this, you can see the bulb is glowing. Okay. If I am moving very slowly, the bulb is not glowing that much. The brightness of the bulb is very weak, and if we are moving fast, you can see the brightness will be more. So basically the Faraday's law of electromagnetic induction is visualized here. Now I will show you the Lenz's law as well. The audio was not there, that's why I am repeating. So here voltmeter is connected. If I am pushing the north pole towards the coil, you can see the deflection. See, the deflection will be towards left side, and if I am taking back, the deflection will be towards right side. See, once again, north pole into the system, deflection towards left side, and north pole out of this coil is coming towards right side. So this has something to do with the Lenz's law, and when you are bringing north pole to this side, the current induced in that will be in such a way that that end will try to become north pole, and north pole on north pole will try to repel, and the system will try to, the coil magnet system will try to change to resist the change of flux, or simply try to stop the motion. We are working against that, okay, and that is the mechanical work we have to do. That work will be converted into electrical energy. Now if you are trying to take out the system, that side becomes south pole, because the current direction will change in such a way that that becomes south pole, and south pole will try to attract north pole, and again because of the attraction the system will try to resist the motion or resist the change in flux. That is the reason why the Lenz's law, that deflection is coming like that. So basically it was interesting in the beginning, if it is moving in one direction, deflection is one way, and other way deflection is other direction. So this is the basic idea behind alternating currents, okay. If you are making an alternating generator, and you can see that the oscillation, the voltage will be changing polarity frequently. So that is the reason behind this. That is I mean, this is the basically because of energy conservation we are experiencing that kind of changes, okay. I hope all of you understood this concept thoroughly. If anybody have any doubt, you can ask at the end of this session, okay. Now I'll do one thing. I will take you to a small problem based on these concepts. It needs some more concepts, actually I will explain, don't worry. So some previous year questions will do. I will give you some time. Yeah, before going to that, see, I wish to talk a little more about our program. You might have experienced that how we are teaching. So basically we show some animation, first some experiments. We will take you through some activity, so that you will understand a lot of details. It's not just like reading your book. You can understand a lot of things, what exactly we are talking, coil, you can see magnet, you can see galvanometer, everything you are able to see. And then if you are learning like that, you will get much more details than just reading or just by hearing the theory. So we are basically working on a method called active learning. Active learning in the sense we are basically involving you to the method of, like you are learning, we are learning together, and you will get lot of detail, lot of information. Then slowly we will take you to the mathematical aspects, so that you will be able to connect the system with surroundings. We'll give you a lot of examples, practical examples, then you can easily connect with the things happening around you. So that kind of learning should be there. Traditionally for decades in India we are doing a lot of by hearting, that is called rote learning. It's very bad. You may not be able to use these concepts in your life. In the sense you can use it for exams and you can do that, you will get a job. But if you want to become an independent thinking person, or if you want to become an innovator, and it's very difficult if you're not able to understand the concept, if you're not studying the concept thoroughly, it's really difficult to reproduce these concepts. That is the basic idea. So our approach is basically to properly give you the concept, so that you are actually learning, not just by hearting. So that kind of method we are following, and we have a R&D team dedicated to develop these kind of activities and methodologies, or we are developing our own pedagogy, so that we can make a revolution in our country. Okay, that is our motivation behind these classes. Okay, I hope all of you understood. If you want to know more about us, you can visit our place, we will share more details. Okay. So I'll give a problem and I will explain first, then I'll give you 2 minutes, and then you try your best to solve this example. And some of this, some need some other concepts. It may not be easy for you, but this is the NEET 2017 question, and try to do yourself. Okay. Here a long solenoid. Solenoid is nothing but we have seen that a coil wound in a the form of a long rod. Okay. So here a long solenoid of diameter 0.1 meter has 2 into 10 to the power 4 turns per meter. Okay, its diameter is given, then 2 into 10 to the power 4 turns per meter. At the end of the solenoid, a coil of 100 turns and radius of 0.01 meter is placed with its axis coinciding with the solenoid axis. So basically you can see that here one coil is there, second coil you are inserting in this form. Exactly this is the problem. Okay, one coil, the larger coil, outer coil is there. Okay, yeah, just a second, I will show you exactly. The camera is setting up, please wait for a second. So we have a larger coil, okay, then a second coil inserting. That exactly based on the problem is based on this concept. So the first coil diameter is given, the number of turns per meter is given. I mean, if you are taking the coil, how many turns are there per meter? Then at the center of the solenoid, a coil of 100 turns and radius of 0.01 meter is placed with its axis coinciding with the solenoid axis. The current in the solenoid reduces to constant rate from 0 ampere to 4 amperes in 0.05 seconds. Okay, if the resistance of the coil is 10 pi square ohm, okay, ohm is the unit of resistance, I hope all of you know, then the total charge flowing through the coil during this time. How much is the total charge flowing through the system? Okay, I will give you 2 minutes, try your best to answer, and please don't stay idle, you try to solve and post your answers. Thank you, we will come back soon in 2 minutes. All right, let us try to solve. Nobody solved. Okay, need lot of concepts. I'll explain one by one. Please listen carefully. It's one of the lengthy question asked in NEET 2017. Not lengthy, but you have to understand the concept. 2-3 concepts you have to mix together. You already know voltage is nothing but, or the EMF generated is equal to d phi by dt. Okay, so change in flux divided by, okay, change in flux divided by dt. Here when you say that the change in flux is actually the total change in flux, including, you have to understand that including that time. Okay, 2 people solved actually in between. Congratulations, Said and Lisa, right? Lisa, okay, congrats for that. So both of you answered. So anyway, we'll explain one by one. Okay, step by step we'll explain. See, in this case, if you are writing this equation, previously we wrote n into d phi by dt. Here n is also included in the total. When we talk about total change in flux, the n is also included here. Okay, that you have to understand. You will get more details when we discuss that. So here, you know that Ohm's law you can apply. Ohm's law is nothing but V is equal to IR. From that you can write down, here what you can write, see, V is equal to IR, or current will be equal to, we can write down, current will be equal to 1 by R into change in flux divided by delta time we can apply. Okay. Now here once again you can see that, just a second, here you can see that change in flux you can find out, and here current, again current is nothing but change in charge divided by, because we have to find out the total charge flowing through the coil we have to find out. So current is nothing but change in charge divided by change in time, delta Q divided by delta time. So here we are going to connect all these things. See, Ohm's law is used, Faraday's law is used, then Coulomb's law actually is actually current is equal to dq by dt, that is also observed, that is also used here. Now we can write down, see, I is equal to delta Q by delta T. So we can write down delta Q by delta T will be equal to, we can say 1 by R into delta phi divided by delta T. Okay. Now you are looking for delta Q, or the total charge flowing through the system. So delta Q you can write down like this, delta Q is nothing but 1 by R into change in flux. Always remember the total change in flux we are saying, the total change in flux in the system. So delta phi divided by delta T, and here this delta T will be coming in the numerator. Okay. Now one more thing, here how to find out the flux, that is the most important point here. The flux, there are two coils, okay. The first coil is there, second coil you are inserting, the number of turns is given and the second coil radius and second coil turns and the first coil radius is given. So how to find out, based on that, how to find out the flux linked with this coil. Now you have to understand this. See here, first coil is there, okay, inside second coil is there. So you already know that when you have a coil like this, there are two coils now. In the first coil, certain amount of current is changing, okay. Some current is changing with respect to time, that is given 0 to 4 amps is changing in an interval of 0.05 seconds, okay. Now you can find out, if that is the case, there is an expression for the magnetic field generated in a solenoid. That is, unfortunately we are not covering today, but it's a basic expression. The magnetic field inside the coil, that you will study in the magnetic effect of current chapter. You studied the basics in the class 10, but the expression, the quantitative expression is not covered at. That is the reason why most of you guys were not able to solve the problem. So B is nothing but, the magnetic field is nothing but at the center of a solenoid will be equal to a quantity called mu 0, is actually a constant called permeability of free space, mu 0 into N into the current passing through the system. See, N is nothing but the number of turns per unit length, that is directly given. So if you are taking a solenoid, total length you take, total number of turns you take, total length also you take, then if you are dividing the total number of turns by length, you will get number of turns per unit length, okay. Now mu 0 Ni is there, you can multiply that with, you are looking for phi, the previous expression you are looking for phi, the phi will be, this is going to give you total change in flux, change in magnetic field, change in flux we can find out by multiplying this with mu 0 into Ni into area. We have to find out the change in area happen to the inner coil. So we have to multiply the number of turns in the inner coil, let us call it N, into the area. Area is nothing but pi r square. See, one important thing you have to understand, if you have only one loop, okay, see something like one loop, then pi r square, that radius area of cross section into that one turn. If you have n such turns, you have to multiply n into pi r square, this will be the total area. So here this is nothing but B and this is nothing but A. So B into A will give you the quantity phi. Phi is equal to mu 0 Ni into capital N pi r square. So if you go back to the previous case, see here this quantity, now we found out this quantity 1 by r into delta phi by delta t into delta t. So we are looking for, all the quantities are given, we are looking for change in charge, okay. Let us try to do that. So 1 by r into, just give me a second, 1 by r into delta phi by delta t, delta phi will replace with this quantity, okay, into delta t. This is nothing but delta q, okay. This is what you have to find out. Now we can write down 1 by r is given, how much was that value? 10 pi square, okay, 10 pi square, 10 pi square into this quantity, change in flux we have to apply, change in flux is nothing but mu 0 into N into I into capital N, that is nothing but the number of turns in the inside coil, into pi into r square. You substitute all values, you will get the answer. So here you can write down this pi, 10 pi square, okay, into mu 0 is nothing but a constant, okay, it's a universal constant, mu 0 is nothing but 4 pi into 10 to the power minus 7 SI units, that you will study in the magnetism chapter, okay, 4 pi into 10 raised to minus 7 units. So here you can write down mu 0 is 4 pi into 10 raised to minus 7 into number of turns is also given in the previous case, 2 into 10 to the power 4, okay, 2 into 10 to the power 4, and current which is unknown, we can write down it as delta I, the variation not unknown, actually delta I we know, delta I by delta t we know, sorry, it's 0 to 4 is changing. So delta I, this delta t I can write down here, here delta t is there, here one more delta t is there, I can write down that delta t here and into delta t. Now we can see you multiplied the mu 0 into n into I into here one more quantity is there, that n into pi r square also you have to multiply. Just a second. Into n into total number of turns n into pi r square. Let us substitute all the values. You can see that 1 by 10 pi square, pi 2 pi's are there because this 2 pi's will cancel out. So pi square will be gone. So 10 into 4 into 10 to the power minus 7 into 2 into 10 to the power 4 into this quantity is 0 to 4 happening in second, like 0.05 seconds. So answer is 4. Here you can say that the change in current will be 4 again divided by 0.05 seconds into 0.05 into 100 into r square. R is 0.01 square you can multiply. See, if you are substituting, solving all answers, you know, you will finally get 32 into 10 to the power minus 6 coulomb, or you can say that 32 microcoulomb. Okay, the answer will be 32 microcoulomb. You can do the math at home, so we are not taking much time. So you can see answer will be 32 microcoulomb. Okay, the pi square will cancel out, that is why pi is not coming. So here this is an example of electromagnetic, all things that we are using is like a JEE question. So here you are using is comparatively lengthy NEET question. Usually you will not get this kind of questions in NEET, especially for last 2 years. Questions are really easy, but you have to practice for all the scenarios. Okay, so here you can say that here first we are using the Faraday's law of induction, then Ohm's law we are using, then this I is equal to dq by dt we are using, then the expression for the field inside a solenoid we are using, then phi is equal to BA we are using. So all these equations you are using, you have to keep in mind all this information, then only you will be able to solve this problem. Okay, I hope all of you understood this. Yeah, next we have a platform called Exam Grid, and right now we are developing that. The last 2-3 days some issue is there, and this platform is dedicated for MCQ questions. You can solve a lot of questions and your progress can be continuously evaluated. Then there is a session for NEET, as well as there is a session for, there is a section for JEE questions. You can practice a lot of questions. You will get immediately, once you submit the answer, you will get the response, your score in SMS, and you can immediately see the solution, and near each question there will be solution written, and you can practice yourself so that you will be perfect. Because mainly NEET exams or JEE exam, you have to practice a lot of questions. It's not only about theory. You have to practice a lot of questions so that you will be able to solve questions in time. So in 1 minute you have to solve one question. So you have to train to that level. That is a key thing, not only about studying theory. Okay, theory will not help you beyond certain limit, like you have to practice. Now, one more question. This is a simple question. Even though this is JEE main question, is simple compared to the previous problem. I will explain the question, try to do yourself, and I will give you again 2 minutes. See, in a coil of resistance 100 ohm, the current is induced by changing the magnet flux through it as shown in the figure. See, the current is changing according to this fashion. So if current is changing like this, how much will be the magnitude of change in flux through the coil is? How much will be the change in flux? Try to do the variation of the variation graph is given. You have to find out answer in Weber and try to solve. I'll give you another 2 minutes. After this, we'll wind up soon. Don't worry, we'll wind up in another 5 to 6 minutes. Welcome back. So Maheshwari answered, then Said answered, then Lisa answered. Congrats. I think a few more people answered, I think. Anyway, congrats, at least you attempted that. So let us see what exactly is this problem. Here again, you have to apply Faraday's law of electromagnetic induction. So you know that electromotive force is nothing but is equal to change in flux divided by change in time. So this is actually the total change in flux by total change in time. So delta phi by delta time. You know, again we can apply V is equal to IR, you can apply, okay, because the resistance of the coil is given, V is equal to IR, or IR will be equal to, or current will be equal to, we can say current will be equal to 1 by R into delta phi by delta T. Here one interesting equation is there. You already know the change in charge, you know, okay. So charge is nothing but, you know, current is nothing but delta Q by delta T. Delta Q by delta T will be equal to 1 by r into delta phi by delta t. You can see that here this delta t we can cancel out. You will get a simple equation. It's a general equation. You can use it for some other problems. So the change in charge in the system when there is an electromagnetic induction, if you have a coil magnetic system, change in charge in the system or the flow of charge in the system will be equal to delta, this one is delta phi, sorry, delta phi. This is delta phi. Okay, delta phi by dt. dq by dt is equal to 1 by r into delta phi by dt. So change in charge will be equal to delta phi divided by resistance. It's a very interesting relationship between charge and flux and resistance. Okay, so very interesting. So please keep this in mind. It will be very useful. You can quickly solve certain problems like this. So here you already know you have to find out the total change in flux. So total change in flux will be equal to, from here you can say delta phi you are looking for will be equal to resistance into delta q. Okay. Now resistance is already given 100 ohms. What is q? Q you already now know that current is equal to dq by dt. Okay. Or we can say dq will be equal to I dt, or we can say that q will be equal to total charge flowing in the system will be equal to integral I dt. Okay. Integral I dt means we can say that is nothing but if you are taking a quantity like this current versus time, if you are plotting, integral I dt is nothing but the area. It's like, you know, area under the velocity time graph will give you displacement, like that area under the current time graph will give you charge. So this quantity, this area if you are estimating, that is going to give you charge. Okay. Now if you are doing that, you can easily find out the answer. So here area will be equal to how much? Half into base into height. So half into, how much is the base? Base is again 1 by 2 or 0.5. Half into base into height is nothing but 10. So this answer will be 10 by 4 or 2.5. So you can say that delta phi will be equal to 10 by 4 into 100 or 2.5 into 100. Answer will be 250 Weber. Okay, 250 Weber will be the answer. I hope all of you understood this thoroughly. This is the key point. This is actually a shortcut. Change in charge or the charge generated or charge flowing through the system will be equal to change in flux by resistance of the system. It's actually not direct equation. Through this, if you are connecting Ohm's law, then dq by dt, then Faraday's law, then only you will get this expression. Okay. I hope all of you understood this question. Now see, we have a program. We wish to share that information as well. See, we have a team, dedicated team to handle the stress in the sense, you know, especially when you are preparing for board exams, a lot of students will face a lot of pressure, you know, in the last moment you have to study a lot of things. That is one case, and in these days a lot of people are suffering from, you know, you may not be focused in studying. A lot of distractions are available in these days. So if you have some problems, we will guide you. We will be giving regular sessions for you how to manage this kind of situation. And not only that, there is a dedicated team for career guidance, and you will get a lot of information what are the future options. So regular meetings will be there, regular webinars will be there, so you can get a lot of updates, and you can, if you are not decided already about your future, about your career, we will guide you. What are the possibilities we will share open in front of you. You can decide based on that. And in the stress management team, we have dedicated team of psychologists and even clinical psychiatrists are there in our team. So if any problem is there, we'll try to solve that, will stay along with you in your journey. Okay. So that is one of our program that you can read in the website. You can read more about that. So here one more thing, we have a software learning management system. It's called UNS e-learning app. We'll be uploading all the videos in that. You know, that is one of the major advantage of online class. See, once, even if you are missing some sessions, sometimes it happens. And even if you are missing, you are not actually missing. You will get a login. You can go back and see your videos so that you are effectively not missing any classes. And not only that, after the class, we'll be forwarding you a lot of DPPs, a lot of notes, a lot of additional videos. Apart from the class, a lot of additional videos will be shared, and all those things you will get access, and you can anytime you can access. Apart from that, your entire progress will be recorded. That if you are weak in certain region, in certain topics, in certain subjects, you can easily identify that. You can take early remedial measures. So these are the advantage of this software. And once you join our center, you will be getting a login, and the entire system will be managed through this system. All right. So if you wish to know more about us, you can either visit, you can talk to, you can call to any of these numbers. You will get direct access to our counselors. They will give you more details, and if you wish to know more details through a direct meeting, you can schedule a meeting and you can come to our center. We will share maximum information about our program, and we will share all other details, all the possible details. Anyway, thank you very much for your time, and hope we will see you soon somewhere. And if